In this video, we're going to learn about titrations. Before really getting into titrations, we need to understand what an indicator is. An indicator is a compound that can act as an acid, and when it does that, it changes from one color to another. So what we can see here is a case of there being a solution of a protonated indicator, and the protonated indicator is going to be yellow in color, but when it gets exposed to a basic solution, it can lose the H plus and turn red when it becomes the conjugate base IN minus. So this form, the red, indicates that we are in a basic solution, and the yellow form indicates that we're in an acidic solution. This is important because if I had a glass of acid and a glass of base, they would probably look like clear colorless solutions without the presence of an indicator, and I wouldn't know which is which. So an indicator can be very helpful in determining or helping us determine whether we have an acidic or a basic solution. And depending on what indicator is used, they can be useful in telling how acidic or basic something is. So let's just go through this image here and try to break it down. Let's say that we have an acidic solution, and there's the indicator in it, like here. We know that the protonated form of the indicator is prevalent and that is yellow. Well, if we add in base, the pH is going to rise and rise and rise and rise. And what that will do is make the equilibrium less in favor of there being HIN, and a little bit more indicator negative will start to become present. And so we'll have a little bit less yellow and a little bit more red. And what happens is that as that becomes noticeable, as there becomes a more noticeable amount of IN minus, you'll start to see orange. And that orange will eventually turn into red as we get more and more red and less yellow stuff present. Again, the red stuff is the IN minus, the conjugate base, and the yellow stuff is the HIN, the protonated form. Now, really important factor is that every indicator has a range of pH values over which that transition will occur. This could happen at a lot of different pH values. It depends on what the indicator is. So what we can do is use titration to determine exact concentrations of an unknown. And I'll get to the point of how do you select the right indicator in just a minute. But a titration is used, you can take, for example, an acid, where you use a pipette to tell exactly how much acid you're putting into a flask. But let's say you don't know the concentration of that acid. You do know exactly how much. Well, you add in a drop or two of an indicator, an appropriately selected indicator, which we'll get to again soon. Then you can put a burette above the flask, and there's an initial reading on the burette, and you can figure out exactly where that line is. And what is in the burette will be a base. So there's a base in here, and that base has a known concentration. So you drop in the base drop by drop, and eventually you get a color change. And ideally, you will stop adding in base at the exact moment that that color change happens and it stays, that you have, that you've gone through the whole titration and you've neutralized all of the acid. And what you can do is you can say, all right, so I started out with this measurement of a certain concentration of base, and I end up with this amount. I can figure out the difference in those two, measure the volume or calculate the volume used. And if I know the volume, and the concentration, which is in moles per liter. So actually, I should change this to, I shouldn't say volume, I should say liters used times moles per liter equals the moles of base used. Whoops. And I can say that's equal to the moles of H3O plus neutralized in the flask that was with the unknown concentration. And from there, I can use the definition of molarity. Molarity equals moles per liter. And I can say that if I had an initial volume of the acid in the flask, and in that flask there were a certain number of moles that I neutralized, then I can calculate the molarity of that previously unknown concentration. It's a stoichiometry problem, and I'll probably make a video on that at a later time. But how do we tell what is the indicator that we should use? Well, in this case, I said that we had, let's say that we have a weak acid and we're using a strong base, okay? So weak acid, strong base. If we have a weak acid initially, after 0 milliliters of base has been added, we might have a pH of around 1. And if we add base, well, oh, sorry, this is weak acid, weak base. Sorry, we should be up here. So we have an initial pH of 3.5-ish. We add base, and the pH goes up. And notice that there's going to be the equivalence point a little bit higher than pH 7. And that actually makes a lot of sense. That makes a lot of sense because, well, let's consider the titration of a weak acid HF with a strong base NaOH. Once we have all of the HF neutralized, you would normally think, oh, that's pH 7. However, look at my conjugates here. This is my base, this is my acid. My conjugate base is fluoride and my conjugate acid is water. We can say that this is basic. And this is not really acidic. We can say that fluoride is more basic than water is acidic. And that comes straight from the K values. So if water is not really acidic and F minus is basic, then when all the HF is neutralized, our pH is going to be a little bit in the basic area. It's going to be a little bit higher than 7. If we were doing a strong acid and a strong base, our equivalence point would be at 7 because we'd have something like HCl plus N, well, I'm just going to say HCl plus, actually, I'll say NaOH. I will say NaOH. Gives us NaCl or Na plus Cl minus plus H2O. We can say that water is not acidic. Sodium ions are also really not acidic at all. And chloride ions are really not basic. So we have nothing here on the product side to really push our pH higher or lower than 7. Again, it's only in the case that we have this fluoride here being a little bit basic that we do get a pH at the end point of the titration that is a little bit off of 7. If you had a strong acid and a weak base, then we might have a pH at the equivalence point being a little bit lower than you would otherwise expect. So you want to choose your indicator based on what the pH will be at the equivalence point. If you think that your equivalence point is going to be, closer to 4, then maybe methyl orange is the indicator that you should use. If you have a case of a strong base and a weak acid, phenolphthalein is usually what you'll use, and that changes actually around in the region of 9. You start to notice it a little bit north of 8. And bromothymol blue is pretty good if you're right around the 7 mark. So you have to choose your indicator based on the type of titration that you're doing. Strong acid, strong base, you're going to be right at an equivalence point of 7. An equivalence point with a pH of 7. But strong base, weak acid, aim for an indicator a little bit above 7 were the changes. And with a strong acid and a weak base, aim for something where the pH is going to be a little bit below 7, where the change occurs, because that will be where your equivalence point is. So I hope this video has been helpful. Let me know if you have any questions or comments in the comment section below. Thanks for watching.